let's take a look at an application that involves the dot product. And in this case, we're looking at work. A child pulls a wagon by its handle across the floor with a force of 30 newtons, upward and to the left, such that the handle of the wagon makes an angle with the horizontal ground of 40 degrees. The child moves the wagon 3 meters. Determine the work done in joules. So in this case, first thing we need to know is that work is equal to the dot product of the force vector and the distance vector. Okay? And so we need to think of the force here as being kind of one vector, and then the movement that happens as another vector. Okay. And when we take the dot product of those two vectors, it'll give us the work. Now, one thing that's important to note here is that, and it's best when we can just look at an example. So we have our little wagon here, and the wagon has some, handle here. I don't know why this wagon is so wavy. Here we go. And so the child is pulling on the handle here. So the child is pulling on the handle, okay, like here. And that's the direction that the force is being applied. But of course we know as this child is, let's not attach its arm to its neck. Okay, that's a little bit better. So here's this large child walking here. Even though the force, right, it's pulling up on the handle, kind of up and over, but the actual wagon is rolling on the ground and moving this way to the left, right? So it's just going like that. So we can think of the force vector here, okay, and we have our distance vector here. And so what I want to do is, now that I kind of have an idea of what this looks like, I'm going to add this 40 degrees in here because there's a 40-degree angle, the handle and the horizontal. So let's then take a look at, let's draw this picture one more time, but kind of in a coordinate plane so that I can kind of think about this. So I see that I have my force vector, and let's think about what I know about it. 30 newtons, that's going to be the magnitude of the vector, so I'm going to label it with 30. And then because this angle here is 40 degrees, the angle in standard position, right, I want to think of it as 140 degrees, and that's the one that I really care about. And then I have this distance vector here that is, it's not going to be to scale because it's 3 here, but that's okay. It is only going to the left, so that's a little bit easier. So let's label these. I have a force vector and I have a distance vector. This is the hardest part of labeling these and finding out the component form. And then once we take the dot product, it works out pretty nicely. Okay, so what I want to do is think about my force vector. How could I write that in component form? Well, I'm going to use the fact that I know the magnitude and the angle to write it using my trigonometric values. So I'm going to have 30 times cosine of 140 degrees I plus 30 times the sine of 140 degrees J. So that's going to be just my force vector. And then my distance vector here, this one's a little bit easier. I don't even need all this like angle and that stuff. Think about where its terminal point would be for a vector that's going just straight left here. This one is just -3, 0, right, that vector, because it would end at the point -3, 0. So how would I write that in component form? Just -3i plus 0j. All right, so now I have these in component form, and even though this is a little bit, kind of funky with, I haven't found approximate values, that's okay. So now what I know is that the work is just the dot product, okay? And when I have newtons for the force and I have meters for my distance, then the work units are going to be joules. So I'll keep that in mind. Okay. So the work is going to be the dot product of the force times the distance vectors. So that means multiply the horizontal components first plus the vertical components. But of course I see something nice happening here. And again, this is just the coefficient. So like the I and the j drop off, right? Because this is really thinking about this like, you know, these values here, right? Like that I would see in a vector without the i's and the j's. So it works out really nicely. I have 30 sine of 140 degrees for my f vertical, but then I have 0. So that's just 0 there. And so again, this is the dot product, right, that I'm applying here, and then these are just little multiplications. Okay, so because this is 0 times here, that's just crosses out that whole term, and so I'm just left with what this would simplify to be negative 90 cosine of 140 degrees. So let's plug that in our calculator. So I'm going to get negative 90 times, make sure I'm in degree mode, I am on my calculator, cosine of 140, in parentheses, I get about 68.94. Oops, 68.94. And the unit here is joules. And again, that happens because I have newtons for my force and meters for my distance. So how did I kind of think about this? Well, I said, which direction is the force being applied? And then which direction is the item actually moving, right? Then I said, let's draw that on a coordinate plane so I can just have a little bit more room. Then I put the force and distance vectors in component form. And then knowing that work is just the dot product of force and distance, those two vectors, then I was just able to find that dot product and know what the work done was in joules to complete that task.